Yes, I am ready.
Okay, off you go.
Right, so this is my talk on escape velocity. It's subtitled New. We will get back to that. So, what is escape velocity? Well, off the bat, it is the velocity required to escape. Pretty simple. It's actually a bit of a coin term. Velocity isn't really accurate because it doesn't matter which way you're escaping from the planet. As long as you've got the speed to escape, as long as you don't hit the planet, you're fine. So velocity is a bit of a coin term. But in any case, all bodies have mass. Everything has gravity. This table, me, have gravity, attracted to each other very weirdly. And so do planets, stars, everything has gravity. Especially with the larger ones we need to escape from, this is more important. So we get many of these ideas from very clever people, most famously known being Isaac Newton, with the famous story of an apple falling on his head, which it didn't actually, it fell near him. He derived this equation, which is the force is equal to gravitational constant times by the mass of our large object we are escaping from, the mass of the object that is escaping, say like us for example, and the distance between the centre of masses of both of those objects. And this is important because this is the force we need to overcome if we want to get escape velocity. So the actual equation for escape velocity is derived using these two equations. We know this for the equation of kinetic energy, and that, even though it is missing an m, I'm not sure why, is the equation of potential, gravitational potential.
Well, that's right for potential, it's not right for potential energy.
Potential energy, yes. Yeah. Because what we are attempting to do here, to escape the influence of a planet's gravity, we need to reach an infinite distance, because gravity hasn't got a finite range. So we actually need v to be 0 to have escaped, and because, assuming no air resistance or other external forces, everything is going to be inkinetic. So we're just going to make these two equal each other. A little bit of rearranging gives us this expression, which is the root of 2 gravitational masses by the mass we're escaping and the surface of the mass. You will see later that the value for this on Earth is about 11.2 kilometers per second, which is a very, very fast speed we need to achieve. Yes, so there you go. Once an object has achieved this escape velocity to actually leave the planet, no further impulse or work is required. It has the energy, it can now slowly bring itself to 0. If it has the exact speed, it will slowly bring itself to the point of infinity and reach 0 velocity. If it has over that speed, it will go past that point with positive velocity. But if we have below it, you're going to fall back to the planet. Sad days. And yes, using the formula, we know that the value on Earth's surface is about 11.2 kilometers per second, which is a very, very fast metric. So what's the problem we experience? We get into space at the moment by firing very large and powerful rockets. These machines expose a lot of rocket fuel to get only very small distances in the air. The problem here comes down to the efficiency of the rockets and the mass that they have in them. And we are going to come down to this guy called Tsiolkovsky. He comes up quite a lot, especially in rocketry. He is dubbed the father of rocketry. Rockets are very wasteful because we run into the problems with mass, as shown in this equation down here that Tsiolkovsky came up with. It essentially dictates that the change in the speed of the rocket that we are trying to lift is due to the exhaustive thrust and the effective thrust by the log of the wet mass, so the mass including all of the fuel of the rocket, by the dry mass, so the mass when all the rocket's been spent. Because essentially a rocket is just a solid holding a bunch of heavy liquid, and this liquid is splurting at the bottom to lift this object up. That's essentially it when it comes to rocket. There you go, you're rocket scientists now. And at the moment, we can all see that it's very inefficient because the ISS alone cost us, mostly the Americans, billions of dollars just to put into a very low orbit around us. So it's not very effective. There is a way that we're hypothesizing on fixing this. There is, again, Tsiolkovsky's come back again. The Tsiolkovsky Tower is a coin term for the well-known space elevator. This will be an object where we will have a counterweight in space connected to a tether, which will connect to an anchor on the Earth itself. And this would actually be able to act as just an elevator. It would ferry things up and down for, I think, it was like 200 pounds per kilogram of goods, which was much better to the millions we saw for those rockets. And it would literally just very slowly take goods up and down. And a very good eco thing about this is we can use the angular momentum of the Earth to, when something has reached the top of the counterweight, just fling it into an orbit for free. The Earth slows down a very, very tiny bit, but it's essentially negligible. We can just get very free energy and just launch like that. However, This is a problem because we don't have good materials such as Kevlar or things that we can actually build this hypothetical device. So in the meantime, we're stuck using rockets. But we're going to get back to that subtitle of Moo. What if we had something on the planet which could actually propel us to a height in space? You've all seen the nursery rhyme, hey diddle diddle, the cat and the fiddle, the cow jumped over the moon. What happened if we actually had a cow jumping and reaching escape velocity? What if we had a bovine assistant? Let us model escape velocities with a cow. So yes, I've gone into the science of it. First off, cows do not in fact have thrusters, as visibly shown there in the demographic. So what we actually have to see is the cow will impart all of its force into the ground in a very deafening jump to actually get to the height. They do fart a lot of methane. I probably could have.
I was about to suggest that, but anyway.
I was going to stay away from a lot of fart power for this. Our cow needs to reach 11.2 kilometers per second, and to simplify this calculation, I've decided to do a spherical cow, if you will, and say the cow will reach this speed 1 meter into the air. If this cow didn't have any form of protection, it would disintegrate. So we're going to assume it has some sort of plot armor or whatever. But the acceleration is very, very, very strong. In order for it to reach 11.2 kilometers a second, a meter into the air, that's the acceleration we get. That would kill anything, it's safe to say. So we continue on, we can now just use our handy-dandy F equals ma equation. We can finally get the force our cow would actually need to push into the ground to achieve such a colossal launch. And yes, my search history is very, very sad because I have calculated the average mass, breed, build of cows, and I got 910 kilograms across all cows. I did my research, and we do get quite a large answer. Ooh. 57 giganewtons of force for that thing to launch itself into space. That's about equal to the energy in 13 tons of TNT. So if you were standing 50 meters away, your bones would be ruptured and you would die. Windows 280 meters around the cow would shatter. So it's not. It's safe to say you'd be very surprised if you heard a very loud moo and your bones breaking. But on those general terms, we don't really have massively overpowered oxen at the moment. We don't have the ability to propel cows, nor is it really ethically viable to propel cows into space. So for now, we must use rocket technology. But they're actually getting some advancements in rocketry. For instance, recently we've had Elon Musk, and he has developed a reusable booster stage. So we used to have to fire all of our stages of rockets into space. They'd be discarded, thrown away, fuel discarded. It's all very, very costly. But now, what he's actually managed to do is we can now make a bit more eco-friendly with some of our rockets and bring them back down to the planet. So whilst it is still very, very costly, we are getting a bit better with what we've got, and it's going to be quite a while before we get cows such as powerful as that. All of the references that I've done in citation of my presentation are here. Are there any questions at all?
Very good.